Self-supervised learning's greatest trick isn't just reducing reliance on human labels, it's learning meaningful representations by inventing its own supervision. Instead of explicit "this is a cat," contrastive learning asks how is this image similar to itself but different from everything else. This core idea trains models to understand intrinsic data structure. The method involves creating positive pairs, two augmented views of the same image, and negative pairs, the original image paired with different images. A neural network, often a ResNet backbone, processes these, projecting them into a latent space. Here's where the Python shines. Libraries like PyTorch with torchvision.transforms are crucial for generating diverse augmentations, random crops, color jitters, or Gaussian blur. The goal is for the model to pull the positive pairs embeddings closer in this latent space while simultaneously pushing the negative pairs embeddings further apart. This is typically achieved using a contrastive loss function like info_nce loss, which maximizes agreement between positive pairs and disagreement with negative pairs. In practical Python implementations, think of it as training a feature extractor without a single human-annotated label. After this self-supervised pretraining, the learned encoder can be fine-tuned on tiny downstream datasets for specific tasks. For instance, in medical imaging, where labels are sparse and expensive, contrastive learning can pretrain on vast unlabeled MRI scans. The learned features then allow a small labeled dataset to accurately detect anomalies or classify diseases with far greater efficiency than traditional supervised approaches. Unlike autoencoders, which might simply reconstruct inputs, contrastive learning specifically focuses on discriminative feature learning, creating embeddings that are highly distinct for different inputs, even subtle ones. This leads to more robust and transferable representations. The implication: we're moving towards foundation models that require dramatically less human oversight in their initial learning phases. Unlocking AI's potential in data-scarce domains like rare disease diagnosis or novel material discovery. Ultimately, contrastive learning shifts our perspective on data's value. It reveals that the true richness often lies not in explicit tags, but in the inherent relationships and subtle differences within the data itself, teaching machines to see these patterns for themselves.